What I want to do now is consider the consequences of what is called resetting a radiometric clock with regard to the rubidium-strontium system, the isochron system that we've already talked about. So first let me draw the typical rubidium-strontium isochron diagram. Okay, here we have the two axes. The y-axis is the ratio of strontium-87 to the stable strontium-86, and the x-axis is the ratio of radiogenic rubidium-87 to stable strontium-86. And remember how this works, that if we had two rocks, or two compositions I should say, let's say two minerals, which initially had the same, since they formed at the same time, they had the same initial ratio of strontium-87 to strontium-86. That's their initial ratio. And I take two minerals here which differ in the amount of rubidium relative to strontium they have. So in an example, I might take one composition here is relatively poor in rubidium to strontium, where the one over here is more enriched in rubidium relative to strontium. And then I allow this rock to age, and as it ages, the concentrations of rubidium-87 and strontium-87 change as rubidium transformed into strontium, and we can show that evolution along this diagram with a line. So this composition would follow a path that looks like this, and this composition would follow a path that looks like this. And so it would ultimately arrive at this point here and this point there, and we said that the isochron diagram is one that is constructed by connecting these two lines together to form a line. I'm sorry, connecting those 2 points to form a line. And that line will intersect the y-axis at the level of 87 strontium to 86 strontium. That represents the initial level. And its slope here will correspond to its age. The steeper the slope, the older the rock. So what we can do is we can measure the concentrations of 87 rubidium to strontium-86 and 87 strontium to strontium-86 in these two different minerals that formed at the same time. And we connect the line, and from that we determine both the initial concentration of 87 strontium to 86 strontium and also the age of the rock, the time that elapsed since the rock began producing more radiogenic strontium-87. Now, what I want to think happened, so let's just make this point again here. This little rock here, this one on the left corresponds to some mineral. Let's just call it a yellow mineral here. This mineral is relatively poor in rubidium relative to strontium, whereas this mineral over on the right dot here corresponds to a mineral, let's say this blue one, that's relatively enriched in rubidium relative to strontium. And it was those different concentrations of rubidium relative to strontium that caused these two compositions to spread out along this diagram along the x-axis and to follow different evolutionary paths, because the rock, or rather mineral that was richer in rubidium-87 produced more strontium-87. That is to say, it traveled farther along this diagram because it was producing more strontium-87 from the larger amount of rubidium-87. Once this has happened now, I want to consider a scenario. What happens now if this rock, which is evolved, the minerals in this rock have evolved to have compositions which lie in this diagram as indicated by the two pink dots. What if this rock now melts? Okay, in other words, physically what happens is, what if I take these two minerals and I heat them up to the point where they melt, and their ingredients just go into the pool of magma and get all mixed up. So what I'm doing is I'm taking all the rubidium and all the strontium and all the different isotopes of rubidium and strontium and putting them all together in one molten pool of magma and mixing them all up. When that happens, we will no longer have two distinct compositions, but we'll only have one composition corresponding to the isotopic composition of the magma. And that magma, which is a mixture of these two purple dots, will have to lie somewhere along this line with a location that depends on the relative proportions of the blue and yellow mineral. Let's just say, for the sake of argument, that it lies over here. In other words, as we melt those two minerals, we produce a single magma composition which has a brand new strontium-87, strontium-86 composition, different than either of the two minerals that melted to produce that magma, and it also has a different radium-87 to strontium-86 concentration as well, right? Because it only has a single one that's made up of a mixture of the two minerals that melted to produce it. Now, so we've produced this magma, and the next thing I want to have happen, let's just extend this out like this, is this magma is now going to undergo crystallization. So it's going to do the exact opposite of what just happened before. Instead of minerals melting to produce a magma, the magma is going to produce crystals, minerals by crystallization. So as this thing crystallizes, it is going to produce brand new minerals. Just leave them like this, open circles like this. A brand new mineral that's relatively poor in rubidium, and it's going to produce another brand new mineral that's relatively rich in rubidium relative to strontium. Okay, so these brand new minerals now are going to form, and what that's going to do is it's going to redistribute the amount of rubidium and strontium in the magma between those two minerals. So the one, let's call it blue over here, one of them over here might be, this is the one that corresponds to this mineral here, the one that's relatively rich in rubidium relative to strontium, and the one that's relatively poorer in rubidium relative to strontium might plot over here. So these two dots, the yellow dot and the blue dot, represent the compositions of new minerals that form after our magma crystallizes. Now notice that, what we said before, both of these minerals have identical ratios of strontium-87 to strontium-86 because the formation of minerals doesn't fractionate isotopes of the same element. They go equally into both of those phases. So both of those phases, the yellow mineral and the blue mineral, have exactly the same initial concentration of strontium-87 to strontium-86. This process here is called resetting the clock. This has reset the isotopic clock. And if now we let these minerals here, these two right over here, these are now solids, and we permit this rock to now age, what's going to happen once again is the isotopic composition of these two minerals is going to change in the same way. So for example, this mineral here, maybe its isotopic composition will change like that. And this one here might change like, oops, I'm going to run out of space here, aren't I? Like this. So it evolves with time from this initial position given by the blue dot to its final position. I'll make them orange here. Okay, initial final compositions given by that and that. So these two different minerals now, after another period of time, then reach compositions, isotopic compositions, which can be plotted as these two orange dots. And once again, we can use the idea of an isochron to connect those two compositions with a line. It supposedly goes, this is the line now, okay? That once again will go through the initial strontium-87, 86 concentration of both of these minerals before they started to accumulate excess strontium-87 by decay of rubidium-87. That composition is given right here. So this point here is the new initial strontium-87 to strontium-86 ratio. And the slope of this line then represents the second period of time that elapsed since the resetting of the clocks. As I've drawn it, it's much steeper than the initial one, so the period, the second period subsequent to their melting, the subsequent period of time is obviously longer than the initial period of time. So what we actually have in this diagram, if this kind of makes sense, if I can sort of follow a composition down, this, let's take a look. I'm trying to find the right color here. Let's do green here. This composition here, this mineral here, initially formed a long time ago. Well, after some period of time, it had evolved to this composition there. then following a melting event, the isotopic clock was reset. In other words, all of the minerals in the rock homogenized, producing a new common isotopic composition, and rubidium strontium composition, which was shown by this value right here. This magma then crystallized, which produced two different minerals with different rubidium strontium concentrations, over to there and over to there, but with, once again, the same strontium 87 to strontium 86 compositions. And then this new rock, the second rock, right, then underwent aging. It aged to the point where we see it now today when we pick it up, and the time that elapsed during that second event is proportional to the slope of the second line, which is the green line. Now, what's the point of all this? The point is that the age we measure for a rock using the rubidium to strontium method, the age we can measure for a rock using the rubidium strontium method is simply the age since when that rock last crystallized. So if the rock has recrystallized, melted, recrystallized, melted, recrystallized, melted many times, the age we will determine from the rubidium strontium method is only the time that's elapsed since it last crystallized. That's not the same thing as the time that elapsed since when it first crystallized. And if we're trying to get at the age of the Earth, not just an individual rock, this isn't going to work, because we know that early in Earth's history, the rocks were continuously remelting, crystallizing, remelting, crystallizing, and every time they remelted, the isotopic clocks were reset. And so there is no way that we will have recorded a rock which was formed, which was crystallized at the time when the Earth formed, because we know that in at least the first 500 million to 1 billion years, the Earth was constantly remelting and crystallizing, remelting and recrystallizing. So the rubidium strontium method is not useful for determining the absolute age of the Earth. In contrast, it has been used to determine the age of meteorites, because the idea is that meteorites formed and then subsequently never remelted. So in the case of a meteorite, we can use the rubidium strontium method, the isochron method, because the time when the rock crystallized corresponds to the time when the meteorite formed. That's not true with the Earth.